Okay, so here we are with our second topic, the tests for the difference between two population means. This independent samples, that's just, we don't need to worry about that. Just if you notice, if you look in your textbook, that's different from what the textbook calls matched samples. So it's just two population means, the same way we've studied population means 2 classes ago. And we're just going to impose the hypothesis testing techniques on population means, or differences between them rather. So let's go straight to this two-tailed equality test. So suppose we have a null hypothesis that population mean 1 minus population mean 2 equals 0. So that is a null hypothesis that there is no difference between these two populations. So suppose the mean income in town 1 minus the mean income in town 2, guess what? They're exactly the same, and that means that the difference between them equals 0. If we're trying to investigate whether or not that's true, we might pose a hypothesis test, as that is the null hypothesis, and we look for overwhelming evidence to the contrary and say, well, the difference between them is not equal 0. So the difference could be a significant high number or a significant low number. And we would construct our two-tailed test based on what we consider a good threshold for unlikely, also known as our significance level, and we would see if a test statistic fell in that unlikely region. If it did, we would reject the null hypothesis and say that the difference between them does not equal 0. Now, we could, and instead of saying 0, just a note, we in this class we will always use 0, but just to put this in context for you, we could say the difference is 5 or the difference is 6,000. That could be our null hypothesis, that the difference between these two means is $15,000. We think that's what it is. And we are going to test whether or not we have enough information to reject that difference of 15, suppose. So we will always use 0, and that will just mean 0 difference, no difference. In other words, the population means are the same. But you could put in any number you want for 0. Okay, and then one-tailed tests would be some sort of assumption. Let's go with this number 2 because I think that's going to be easier to understand. This null hypothesis, the population mean 1 minus population mean 2 is greater than or equal to 0. So that means it's a positive number. So income in town 1, we think it's 70,000. Income in town 2, we think it's less than that. Maybe it's 69,000, maybe it's 50,000. So that would leave, whatever. So if this was 70 and this was 59, that would mean 11,000 would be the answer to this. Population 1 minus population 2 would equal 11,000, and that would be greater than 0. And what we're saying is we think the population mean in town 1 is higher than the population in town 2. That's all we're saying by this 1 minus 2 is greater than 0. So we might think that. Someone else might say, well, let's set up a hypothesis test to see if we can disprove that, and then we just flip the sign. We say that that is less than 0. That if we take population mean 1, subtract population mean 2, we're going to get a negative number, meaning, in fact, the average income in town 2 might be bigger than the average income in town 1. So the bigger number minus the smaller number would be less than 0. So, and it's the same way we would say, we're going to operate under the assumption that the null hypothesis is true. The alternative hypothesis is the opposite of that, and we're going to see if we find overwhelming evidence to disprove the null. And finally, so this, if we want to set up the test, the population mean in town 1 minus the population mean in town 2 is less than 0. We might be saying, hey, this town has a lower income then town 2, all the poor people live in town 1, all the rich people live in town 2. So when you take the average income in town 1 minus average income in town 2, you're going to get a negative number. And then someone comes along and says, wait a minute, no, that's not true. I think it's the other way around. So let's look for evidence and see if we can disprove your null hypothesis. The z-statistics are going to be set up the same way. If it's a one-tailed test, there's going to be the z-critical values, well, both. The z-statistics and the z-critical values are going to be set up the same way. And if it's the z-stat falls in the rejection region, we reject. P-value approach, same way as well. If it's a one-tailed test, we're going to find the area under the curve associated with that z-stat, and we're going to double it. If it's if it's two-tailed, I don't remember what I said. But let me just repeat that again. If it's a two-tailed test, we find the area under the curve and double it. If it's a one-tailed test, we find the area under the curve and we do not have to double it. Same rationale, same logic as before. Okay, now what is going to change is just the way we calculate our z-stat, because we have a slightly different standard deviation metric. So let's move on to that. Alright, so if we're calculating mean differences, the key tool is going to be our sampling distribution of the sample mean difference. We take the difference between town 1 income, difference between average income and town 2. We do that 10,000 times. We put it all in a frequency distribution. You are going to get this sampling distribution of sample means. And God be praised, that is going to be normal. And when I say God be praised, I'm not saying anything religious. I'm just saying we are happy about that, because if it is normal, we can make all sorts of assumptions about what the data will look like. So the sampling distribution of the sample mean has a mean which mirrors the true population mean difference. All right, we're most likely going to get the actual difference between town 1 and town 2. And it's going to have a standard deviation, which we can calculate based on the standard deviation of the population in town 1, population in town 2, and divide by sample size. So the bigger sample size, the tighter this distribution is going to be. So we're going to calculate our test statistic using our sample data, when we sample from town 1 and town 2, and this standard error figure. All right. Suppose we're setting up a two-tailed test. This is our sampling distribution of the sample mean difference. Suppose we were looking at a significance level of 5% in this example. Significance level 0.05. And it's a two-tailed test, so we start with some inequality. There's some equality. And that the difference between population 1 and mean and population 2 equals 0. It could be disproved one of two ways. It could be, our sample could be really high or really, really low. And we would have 2.5% in either tail. If we have 5% in either tail, we have 1.96 plus or minus as our critical values for our rejection region. Alrighty. Now, how do we calculate our test statistic to determine whether or not that test statistic falls in the rejection region? Well, the first thing, we go out and we take some sample data. Sample data, this is sample mean from town 1, this is sample mean from town 2. We find the difference between those two. And then we subtract off 0, because as you recall, in all of the tests we use in this class is we're going to use a null hypothesis that the difference is equal to 0 or the difference is greater than 0 or less than 0. We could use other numbers. I gave the example, we want to test a null hypothesis that the difference is 15,000. So we could put 15,000 there if we wanted to, but for our purposes, as we get used to this, we're just going to say the difference is 0. So let's see. So we're going to find out how different. So if this difference, all right, so this is town 1, this is town 2. So we do a sample of town 1 and we get, say, I don't know, 70,000 for income. And we get town 2 and we get, say, 59,000. The difference between that is 11,000. And we want to find out how many standard deviations 11,000 is above the mean that we would expect under the assumption that your null hypothesis is true. And then this minus 0 because we're just saying how different is it from 0. Okay, so this is our sample data. This is based on our null hypothesis of saying 0 difference. And then we divide by the standard deviation of the sampling distribution of sample mean differences. And we know that formula. Okay. All right, now, since we do not necessarily have the population standard deviation all the time, when population standard deviations are unknown, we theoretically do two things. One, we substitute in the sample standard deviation. The other thing we might do is use the t-statistic. And as I mentioned when we did mean differences the first time, I said you could use the t-statistic. You could use that slightly higher numbers that are associated with the t-statistic to add a little extra padding. But statisticians are comfortable with using the z-table when we do mean differences. And the reason for that is because there's just more moving parts. They say, all right, look, as long as we have a sample of 30 from population 1, a sample of 30 from population 2, maybe they're going to be a little bit off, but there's more numbers involved, and there's a greater chance that any abnormalities are going to cancel each other out. So we in the case where we do mean differences, both when we're just doing mean differences for trying to calculate a confidence interval for mean differences, and now that we're doing hypothesis testing for mean differences, we're good with using the z-statistic. So to get the sample standard deviation of the sampling distribution of the sample mean difference, or standard error of the sampling distribution of the sample mean difference, we substitute in our sample standard deviation for population 1, population 2, sample size 1, sample size 2, and we take the difference and our mean differences and we divide that by the number of standard deviations that we calculate. All right. Let's do an example.